Slide. Again, the vertical cross-section of the MOSFET, and as you're aware by now, we have to have a field plate action using the overlap of the gate metallization over the drain region as it approaches the oxide interface to prevent a sharp radius of curvature from causing lower breakdown voltages than we had designed for based on a plain parallel depletion layer boundary. The thickness of the drift region, which I'm indicating here, and the doping density N minus is determined by what the breakdown voltage rating for the MOSFET is. And what we want to do is make sure that we use the device wisely and make sure that under all circumstances we don't exceed that breakdown voltage rating, and in particular if there are inductances in series with the MOSFET that may cause overvoltages, we may have to consider the use of appropriate snubber circuits. The MOSFET on-state losses have several contributions. If we're talking about a low voltage MOSFET, something on the order of 100 volt or at most breakdown voltage, then the contributions to the on-state losses come from all parts of the device. There is the resistance of the source diffusion that I've indicated, the resistance of the channel, so-called accumulation layer resistance, which is where the current is now in the drain region but begin to bend over from being horizontal to the top surface to going vertically. There's the drift region contribution, and finally the drain region contribution. All of these are perhaps equally important at low breakdown voltage ratings. As you increase the breakdown voltage rating of the MOSFET beyond 100 or so volts, then the drift region dominates the on-state resistance. And one can show in a simple calculation that the on-state resistance in silicon MOSFETs at these higher breakdown voltages is proportional to this numerical factor, 3 times 10 to the minus 7 times the square of the breakdown voltage divided by the cross-sectional area of the drift region through which the current is flowing. This on-state resistance increases as temperature increases due to the fact that the mobility of the carriers goes down as we increase the temperature of the silicon. It's possible to put high voltage MOSFETs in parallel and thus come up with a composite device or system that can carry significantly more current. And that's shown in the next slide. The reason that we're able to do this is because of the positive temperature coefficient of the on-state resistance. This gives us a thermal stabilization effect. For example, if the resistance in on-state resistance of Q1 is larger than the on-state resistance of Q2, which I'm just putting in a symbol for now, then more current, and thus there will be higher power dissipation in Q2. But as a consequence of this, the temperature of Q2 will increase, perhaps higher than the temperature of Q1, and thus its on-state resistance will become as large or larger than that of Q1, and so some of the overcurrent that was there temporarily will go back to Q1. And so we have this thermal stabilization, which makes it much easier to consider paralleling MOSFETs. Some bipolar devices have a negative temperature coefficient, which means as one of the devices in parallel gets hotter, it has a better conduction characteristic and takes even more current, and thus hogs most of the current, and that can lead to thermal runaway, a positive feedback situation. The next slide here that I've just brought up is the MOSFET safe operating area. This is sort of a summary of some of these limitations that I've been talking about for the last couple of minutes. It's a plot of the drain current as a function of the drain to source voltage. The maximum drain current, I sub dm, is not a thermal limitation. It's due to a limitation on how much current density you can have either in the thin film metallizations that contact the diffusions or the bonding wires that connect the thin film metallizations to the outside world. If those current densities get too high, we can blow apart the conductors. In other words, they can act as a fuse, and so that's the source of the maximum drain current. The maximum drain to source voltage is the BVDSS, and that's this vertical line that you see on here. The slanted line, about 45-degree orientation, is a thermal limit. If we have very slow switching speeds, or basically if we're operating at almost DC conditions, then we have a fairly limited safe operating area, because what is happening is there's a maximum temperature to which we can subject the interior of the silicon. Typically that maximum junction temperature is on the order of 150 to 175 degrees centigrade. If it gets hotter than that, then you're exceeding the ratings that the manufacturer guarantees, and you're at the very least compromising the reliability of the device quite severely, and you may even lead to failure. So the safe operating area in this condition is this shaded area that I'm indicating here. Any load line within this safe operating area is legitimate. So this would be a safe load line. If we had a load line that was outside of the safe operating area, such as this one or this one, the first one here is too much current flow. This one we exceed the breakdown voltage. And so we want to make sure that our load line stays within the safe operating area. Now fortunately for us, we're not limited in power electronics by the DC condition. We're limited by how fast we can switch. And so what I'm showing here is if you can switch the device on and off progressively faster and faster, here I'm talking about a millisecond, 100 microseconds, less than 10 microseconds, you can approach then a larger safe operating area that's basically square, set by ISIP-DM horizontally and BVDSS on the vertical side. And so that's why we try to operate these devices as fast as we can in making the transition from being off here to being on here, or going the other way from being on to being off. We want to make the transition through this active region where we have a combination of large voltages and large currents, which means high instantaneous power dissipation. We want to pass through that region as rapidly as possible. The last topic I want to take up in this video is a comparison of the standard vertically diffused MOS MOSFET with I think I'll terminate the discussion of MOSFETs here. This last topic is somewhat specialized on superjunction MOSFETs. These devices are capable of going up to 900 to 1,000 volts and carrying several tens of amps of current. And it's a modification of the basic MOSFET structure. And for those who are interested in it, you can look at that at your leisure. But in the interest of time, I thought I would terminate the discussion here. Doesn't seem to be any questions on MOSFETs. So in the interest of time, I will now do the last of the 4 modules I was going to talk about, and that is the wide bandgap devices. This is sort of a summary of what the current situation is in wide bandgap devices and how they compare favorably with silicon devices. So let me first go to the appropriate let's see, gotta find it here. Things aren't quite alphabetical, or there we go. And the next thing I need to do is
about wide bandgap devices for power electronics.
Share this.
I'm going to cover, shown in the outline below. I'll first discuss why silicon devices are going to be inadequate for future
applications. I'll then talk about the wide bandgap materials that will offer improved devices. I'll do some comparisons between silicon and wide bandgap devices. I will then talk about a relatively new power electronic device, the gallium nitride high electron mobility transistors. And then finally I'll conclude with what present day wide bandgap devices capabilities are and a look ahead. This chart shows the approximate power capabilities of present day silicon devices. It's a complicated 3-axis plot. On this side, I have blocking voltage capability up to 5 kilovolts. Along the horizontal axis, I have the on-state current capabilities out to about 3,000 amps. And along this axis, starting from the back and coming forward, if you like, sort of out of the page, I have the switching frequency capabilities. The highest power devices are thyristors and related devices. However, they're quite slow, and so they appear here at the back of the presentation. GTOs and some of the related devices like integrated gate, commutated thyristors, and emitter turnoff thyristors have somewhat higher switching frequency capabilities, but they're not quite as high a blocking voltage or on-state currents. IGBTs are sort of the workhorse of modern-day power electronics. Their capabilities span a wide range of blocking voltages, on-state currents, and switching frequencies, up to several tens of kilohertz. To go beyond about 100 kilohertz, about the only device that is capable in the silicon family are MOSFETs, and they have capabilities up to about a kilovolt and frequent and current capabilities up to 50 or perhaps 100 amps, but their switching frequency capabilities go out to megahertz and higher. The reason why I make the statement that silicon devices are inadequate for future applications is the technology is fairly mature. I expect only minor evolutionary improvements to occur in the future. Unipolar silicon devices like MOSFETs and Schottky diodes are used for high frequencies up to hundreds of kilohertz and voltages up to perhaps 1,000 volts. Bipolar devices like SCRs and IGBTs, PIN diodes are used for higher voltages, 1 to 20 kilovolts, but their switching frequency capabilities are significantly lower. Furthermore, silicon devices are limited to junction temperatures of no more than 150 to perhaps, if you're optimistic, 200 degrees centigrade. However, power electronic applications are pushing the boundaries to higher voltages, higher operating frequencies, higher temperatures, and higher efficiencies, in some cases all simultaneously. Silicon device usage in these future applications is going to be increasingly difficult and expensive. Fortunately, wide bandgap power devices offer potential solution. These devices are better than silicon power devices, especially for high voltage applications. They are faster, have lower losses, and higher operating temperatures. Now, wide bandgap devices operate by the same physical mechanisms as silicon devices, and their device geometries are quite similar to corresponding silicon devices. Hence, the better performance that we get out of wide bandgap devices is due to the superior material properties, which I'll discuss in a bit more detail in a moment. Wide bandgap materials that are currently of interest include gallium nitride, silicon carbide, and perhaps in the more distant future, diamond. The reason for the interest in these wide bandgap materials is sort of summarized in this table of material properties. I list 4 materials, including silicon carbide, gallium nitride, and diamond. Bandgap. Wide bandgap materials are significantly higher bandgaps than silicon, 3.2 for silicon carbide, 3.4 for gallium nitride, and 5.5. I list the relative dielectric constants, and they're similar. Diamond is about a factor of 2 smaller. Their saturated electron drift velocities are similar, diamond having the highest saturated drift velocity. Thermal conductivities. Silicon is only about 1.5 watts per degree C centimeters. Silicon carbide is 3 to 4 times better. Gallium nitride is a couple of times better. Diamond is significantly better. And this higher thermal conductivity means it's easier to get heat that is dissipated in these devices to the outside surface of the device. The intrinsic carrier densities of the wide bandgap materials are significantly smaller than those of silicon, and this implies then higher operating temperature capabilities. Mobilities of all these materials, particularly for electrons, are quite similar. Hole mobilities are also similar. The main factor that plays into why semiconductor materials that have wide band gaps are make better devices is in the breakdown field strength. Silicon is only about 300,000 volts per centimeter. All of the rest are at least an order of magnitude larger, and as we're going to see a little bit later, this is the prime factor that makes the wide bandgap materials superior devices for power electronic applications. For example, let's consider a simple example of calculating the blocking voltage capability of a PN junction. I'm assuming a one-sided step junction. It's not too difficult to show that the breakdown voltage is proportional to the square of the breakdown field strength divided by essentially the doping density, and the drift region thickness has to be greater than twice the rated breakdown voltage divided by the breakdown field strength. And if you look at the table here, I'm assuming equal breakdown voltages for all four types of materials. And what we see is doping density in silicon has to be quite small, 6 times 10 to the 14th. The other materials can be a couple orders of magnitude higher, which means significantly lower on-state losses. The width of the drift region, or length if you like, is pretty long in silicon, 67 microns. All of the others are at least an order of magnitude smaller, with the smallest being in diamond. Smaller drift region lengths, of course, also mean smaller on-state losses. Going forward, if we do a comparison of the on-state resistances, the figure of merit is usually the on-state resistance times the area of the current that is flowing through that resistance. The area of the device through which the current is flowing. This is the so-called ohms per square. And if the drift region is the dominant factor in on-state losses, it's fairly simple to show that an approximate formula for the losses for the on-state resistance is given by this formula. It's proportional to the square of the breakdown rating and divided by the cube of the breakdown field strength. If we normalize that to silicon and assume the same breakdown voltage for all types of devices, similar devices made out of the four different materials, the on-state resistance ratio in silicon it's 1. Silicon carbide is about 10 to the minus 3. In gallium nitride it's 4 times 10 to the minus 4, and in diamond it's 4 times 10 to the minus 5. Again showing why the breakdown field strength is the most important thing in determining on-state resistance and thus switching losses, conduction losses. If you do a comparison for a bipolar device, one can show approximately that the ohms per square of the on-state resistance is given by the formula that I'm showing here, breakdown voltage divided by breakdown field strength, and 1 over the approximate excess carrier density. If we normalize to silicon and assume the same breakdown voltage and same excess carrier density, again I calculate the ratios, and again the wide bandgap materials show superior performance. Higher operating temperatures of the wide bandgap devices are basically due to the fact that wide bandgap means that the intrinsic carrier densities are much smaller. Here I have a table of different junction temperatures, and for each of the four major materials that we're considering I show the intrinsic carrier density. And even at elevated temperatures as high as 1,000 degrees, silicon carbide has an intrinsic carrier density of 3 times 10 to the 14th. Diamond is about 1.7 times 10 to the 13th, whereas silicon is 10 to the 18th. The problem with this is, as the intrinsic carrier density gets larger than any of the doping levels, you're essentially shorting out the PN junction. The PN junction reverse saturation current is proportional to Ni squared, and so it's going to increase significantly as the junction temperature increases, even if you haven't reached the value of intrinsic carrier density that shorts out the PN junction. In addition, the drift regions develop a positive temperature coefficient, leading to possible thermal runaway when Ni at the given temperature exceeds the drift region doping density. In practice, the temperature limits are going to be probably significantly lower and set by packaging, interconnect and reliability issues, phase changes, thermal stresses, and the temperature limitations of other components that are used in conjunction with the power device itself, such as capacitors or inductors. Switching speed comparisons. If we do a bipolar comparison, I show here a PN junction, PIN diode, forward bias with some current I. The excess stored charge in the drift region is approximately I times the carrier lifetime. The drift region length has to be approximately or somewhat smaller than the diffusion length, which is the square root of the ambipolar diffusion constant times the carrier lifetime. If you invert this equation, I have 1 here now for the carrier lifetime, and the ambipolar diffusion constant is defined in the next equation. And the drift region length is also given here by twice the breakdown voltage divided by the breakdown field strength. Putting all that together, you can show that the saturation, the excess stored charge is given by the current times these other parameters. And the thing to note is that it's proportional to the square of the breakdown voltage and this over 1 over the square of the breakdown field strength. If we compare a silicon diode with a wide bandgap device, one can show that for the same current and the same breakdown voltage, and assuming the mobilities are the same, the ratio is basically of the stored charge in the wide bandgap material divided by the stored charge in the silicon device is proportional to the square of the breakdown field strength of silicon divided by the breakdown field strength of the wide bandgap device. And this is going to be much less than 1. And so the wide bandgap diode will switch much faster than a silicon diode using the same drive circuit. And similar reasoning would apply to IGBTs and other bipolar devices such as GTOs and thyristors. If we wanted to estimate a comparison for unipolar devices like MOSFETs, here's a single cell of a MOSFET which shows all of the parasitic capacitances that make up the device and contribute to the switching time capability of the device. If we assume that we're talking about, say, a very simple buck converter circuit, then we can make some analytical estimate if we wanted to of what the switching times would be. I'm not going to do that in this particular presentation, but I would point out that all of these capacitances are what are a major determinant of the switching speeds of the device. And these capacitances are proportional to the overlap area that I've defined here, which is the approximately the area through which current flows through the drift region. The area of a drift region for a wideband device is much less than that of a silicon device if you assume the same drift region resistance. And if we're thus using the same driving circuit, the WBG device will switch much faster than the silicon. The conclusion is wide bandgap devices are faster than comparable silicon devices, primarily because the much larger breakdown field strength allows the cross-sectional area of the device, of the wide bandgap device, to be much smaller than that of a comparable silicon device, thus much less capacitance, or in the case of bipolar, much less stored charge. If we can make a qualitative comparison between conduction and switching losses, conduction losses in bipolar devices are dominated by the on-state resistance, and if we assume identical devices, that is breakdown voltage and cross-sectional area and excess carrier density, the smaller drift region length means that the wide bandgap device is going to have low HIMT transistor. The device is smaller, particularly the area of the drift region. One of the new devices that's possible with wide bandgap materials for power electronics is the GaN HIMT transistor, HIMT standing for High Electron Mobility Transistor. This slide shows the basic structure in a simplified manner of a so-called lateral gallium nitride HIMT transistor. The device is made starting with a substrate of either silicon, silicon carbide, or sapphire, and then MOCVD or MBE is used for device fabrication. One of these two techniques is used because it gives you great control over the vertical thickness of the various layers. So on top of the substrate, we grow 1 to 2 microns of semi-insulating gallium nitride, then about a 30 angstrom thick layer of insulating or intrinsic aluminum gallium nitride, and then another 30 angstroms or so of heavily doped N-type aluminum gallium nitride. And then windows are opened up for the source and drain contacts, which are ohmic contacts, and then also a rectifying contact for a Schottky barrier contact for the gate. The drain and source metallizations have to be especially picked to get the ohmic contact, and similarly for the gate metallization. High voltage capability requires that the distance between the gate and drain be 5 to about 15 microns. Right now, 600 to 900 volt blocking capability devices are commercially available with on-state resistances of 10 milliohm and ohms or less. The device which is shown here is normally on, but normally off devices have been demonstrated in a lab by making structural and doping changes. The on-state operation of a device occurs when you have zero gate to source voltage, because this is a normally on device. In that situation, the electrons which are in the N+ aluminum gallium nitride near the interface are able to diffuse across and into the intrinsic gallium nitride. And the reason for that is the average energy of the electrons in the N+ aluminum gallium nitride are higher than that in the gallium nitride layer, and so they just naturally will diffuse across. This forms an accumulation layer at the interface between the spacer layer and the aluminum and the intrinsic gallium nitride. And the density of the electrons here is so high that it's sometimes called a two-dimensional electron gas. Numbers that are often quoted are 10 to the 13th electrons per square centimeter. The accumulation layer or two-dimensional electron gas is a very low resistance channel between the drain and source. And the device, as I've already shown, is a normally on device. The spacer layer is essential because what it does is it separates the free electrons in the accumulation layer from the aluminum gallium nitride, which is heavily doped. And this is essential because without the spacer layer, the ionized donors that are right at the interface would influence the mobility of the electrons in the two-dimensional electron gas and greatly lower their effective mobility. But by having a spacer layer here, we greatly diminish the influence of those ionized donors, and so the electrons in the accumulation layer or two-dimensional electron gas take on essentially the same mobility as electrons in the intrinsic gallium nitride bulk, and that is significantly higher than the mobility in the N+ aluminum gallium nitride by a factor of 4 or 5 or more. Vertical GaN devices are under development that in principle should have much lower on-state values than the lateral devices. However, those are not yet ready for prime time, and so further development is going to be required. In the off state, what one has to do is reverse bias the gate to source junction, as I've shown here. And if the negative gate to source voltage is larger than the so-called pinch-off voltage, this will create a depletion region that I'm showing here that will block the current through the two-dimensional layer, and so no current will be able to flow from the drain to the source. The main requirement for a large voltage rating is that the distance from the gate to the drain be large enough to accommodate the lateral growing depletion layer without the depletion layer boundary hitting the drain metallization, and thus implementing punch-through. In order to do that, field plates are usually required in order to shape the electric field properly within the depletion region, but I haven't shown the field plates for simplicity. There are other secondary factors like interface traps and the possibility of vertical breakdown between the drain and the substrate if the substrate is grounded, as the source might be, but that can also affect and lower the breakdown voltage capability. But this is getting into details that are beyond the scope of this particular presentation. Well, now we come to a question: if these approximate model calculations have any validity, then there probably ought to be a variety of wide bandgap devices commercially available, and that is indeed true. I did a quick search using Google and came up with the following list of devices: a MOSFET normally off enhancement mode using gallium nitride, 600 volt breakdown, 52 millimos for the on-state resistance, current capability 36 amps. Another MOSFET, this time silicon carbide, up to 1700 volts was available, had an on-state resistance of 1 ohm and 3 amp capability, at 1200 volts, 25 milliohms, on-state resistance, 60 amp capability. And you can perhaps read the rest of the chart. There's a bipolar junction transistor at 1700 volts, 45 amp capability, a thyristor, silicon carbide at 6500 volt blocking, 6 millimos, 80 amp capability, normally on JFET silicon carbide, similar capability as the MOSFET enhancement mode, Schottky diode at 1700 volts, 25 amp capability, forward voltage 1.8 volts. A PIN diode silicon carbide at 8000 volts, 2 amps. A half-bridge module made out of enhancement MOSFETs, silicon carbide, 1700 volts, 225 amp capability. I use the asterisks up here after the word commercially because there are part numbers for all of these, but it may be that they're fairly preliminary and it may be difficult to obtain some of these devices that are so-called commercially available. Looking at more demonstration devices in the research laboratory, here is a 10 kilovolt PIN silicon carbide diode at 100 amps per square centimeter, which corresponded in this case to about 50 amps flowing. The forward voltage was about 3.7 volts, and it goes on up from there. The blocking voltage capability, when you went out to a reverse voltage of 8000 volts, the leakage current was someplace in the neighborhood of a few hundred microamps. This chart shows the forward bias capabilities at various temperatures: 100 amps per square centimeter, 400, 2000. Here are the various temperatures, and the thing to note is all of these track very well together as a function of the forward voltage, and thus paralleling these as a function of temperature would seem to be possible. Turn-off behavior is quite fast. Here we're going from 100 amps per square centimeter at a forward voltage of 4 volts with a dIdt of 330 amps per microsecond, and it turns off starting from this point something on the order of about 200 nanoseconds. And so we're talking about a fairly fast turn-off for this high voltage device, and it's showing it at different temperatures, and it seems to be relatively independent of temperature. Here are some other examples of devices that I found doing a quick search. Junction barrier Schottky diodes at 10,000 volts, a PIN diode at 4,500 volts, 180 amps, 3.2 forward voltage, a vertical MOSFET at 10,000 volts, 10 amps, an N-channel IGBT at 12,500 volts, on-state resistance of 5.3 millimos, a commutated GTO at 4,500 volts, 120 amps, a bipolar junction transistor in silicon carbide at 4,000 volts and 10 amps, a normally off JFET and gallium nitride, 100 amps at 600 volts and 9 millimoles, and you can read the rest. There's even a diamond Schottky diode at 10,000 volts, but I couldn't find any other information about it. So what does this all mean? I think we've convincingly demonstrated that wide bandgap devices are fundamentally superior to silicon. The basic reason is the 10x or more larger breakdown field strength that enables faster switching with lower losses. The larger bandgap enables higher operating temperatures, and the larger thermal conductivity provides the ability to dissipate more power in the device without exceeding the temperature limitations. There are a variety of commercial silicon carbide devices available, and they're going to dominate power electronic applications probably above 1,000 volts in the future. Gallium nitride devices are theoretically somewhat better than silicon carbide, but lag in availability, basically because vertical gallium nitride development has been hampered by a lack of large, inexpensive gallium nitride wafers. From a fundamental viewpoint, diamond would be the best material for power devices, but the lack of large, inexpensive single crystal wafers is hindering their development. In my estimation, it's going to be 10 or 20 years before there's any diamond devices commercially available, and it may be longer. It's going to be a function of the technology development in making large single crystal diamond wafers. Thank you for your attention. Okay, that finishes the presentations that I was going to give. As some of you have already commented, this is a very large dose of semiconductor device physics and explanations of how these devices work. Whether or not a particular course ought to go into such depth is a function of the instructor's goals in teaching the power electronics. At the undergraduate level, I would certainly say, no, you don't want to go into this in any great detail at all. Just give them the terminal characteristics, unless you have more than one power electronics course at the undergraduate level. At the graduate level, yes, it's probably useful for those students who are going to go on to do detailed graduate work in the power electronics area. If it's only for a master's degree, maybe not. I don't know. That's a very subjective opinion. Here at the University of Minnesota, we have decided that it's useful to have all of these devices described in the level of detail that I've gone through. In the 3 or 3.5 hours that we had today, I could only illustrate a couple of the presentations that we make use of, but I went through nearly the complete duration of all these videos to give you the impression of how much depth we go into. And all of the other devices are dealt with in a similar way. Whether or not you want to get into that is a function of the particular goals that you have when you're teaching a course. For those of you who are more listening as interested observers, and perhaps I'm not doing any teaching, hopefully this is useful to you. At the very least, all of the discussions and videos and other things that I refer to are available on the CUSP website to anyone who wants to look at them. The only thing that's not available to the general public is the detailed homework solutions, and for that you have to be a member of CUSP. And information on how to become a member is given on the CUSP website. As far as last minute questions, I think there was only one. Okay, I guess there's two. Could I comment on COSS losses in gallium nitride HEMTs? How much of a trade-off is there when comparing gallium nitride advantages? To be honest, I don't think I'm in a position to comment very much on that. I've never used any of these devices in a practical situation because my area of research has not been in power electronics. I have to admit I know just enough about power electronic circuit design to be dangerous. It's a long story as to why I'm affiliated with Ned Mohan and the textbook that he and I and Tori Undelin wrote, but it was more a question of over a period of time, we developed a series of lecture notes, and sooner or later, the idea occurred to Ned we ought to write a textbook, and so the camel got his nose in the tent, and the rest is history.
but I am not enough of an expert, as I said, on power electronics to probably comment on that. The other question is, I mentioned paralleling MOSFETs. I'm curious about paralleling IGBTs. Do IGBTs have a positive or negative coefficient? The answer is IGBTs are a bipolar device. We are putting, basically an IGBT is a MOSFET, and then we put an extra PN junction between the anode and the top of the drift region. So you have a 4-layer structure in a IGBT instead of a 3-layer structure for a MOSFET. So an IGBT is basically starting at the anode, it's P, N-type drift region, P-type body region, N-type source. And so it's a bipolar device. The basic idea is we flood the lightly doped drift region with a lot of excess carriers. And so we have a MOSFET-like input, but we have a bipolar transistor-like output. And some of that comes out when you look at the circuit symbols for IGBTs. In some cases, they use the collector and emitter terminology for the output terminals and a gate for the input terminal. Other people talk about a drain and source of an IGBT and a gate at the input. So even the technical community hasn't really settled completely on how to describe an IGBT. But it is basically a bipolar device, and so it has the same problem as other bipolar devices. And that is, as the temperature goes up, the intrinsic carrier density goes up, and your possibility you're going to have a positive temperature coefficient situation, so that the resistance will be going down as the temperature goes up. And so that's the possibility of thermal runaway. Now, this is not a deal breaker by any means, particularly when people make the very high current IGBT modules. They are putting various IGBT chips in parallel inside the package. And what they have to do is they sometimes have to put a small amount of resistance in series with each of the chips in order to create an overall negative temperature coefficient. And so it is possible to parallel them, and in fact, manufacturers do that for you when they make these high current modules. As to whether or not you want to go beyond that and take a lot of these high current modules and put them in parallel, though, then you're going to have to be quite careful about what you are doing and making sure that you choose a small amount of series resistance in series with the source, or if you like, the emitter of the output terminals, so that you can have essentially a negative temperature coefficient. Let's see, are there any other questions? Well, that seems to be all of the questions that have been submitted. I have almost 4:30 now, so I think we're at the end of our allotted time. You have been very patient in listening to a lot of material that a lot of you probably are not as familiar with as you would think you needed to know about. But I hope you found it interesting, and I encourage you, if you have the interest and the time, to look at some of the other videos on these the other devices. As far as where you can get more details, the textbook that Ned Mohan and I and Tori Ellen wrote has all of these details, the 3rd edition. Another very good book that gets into a lot more detail than you'd probably ever want to get into is one of the books by Baliga. This one is Power Semiconductor Devices. This is a 1996 version where he goes into all kinds of detail on all of these devices. He recently has another book out called Fundamentals of Power Semiconductor Devices, which is copyright date of 2019, where he'll have some discussion of silicon carbide devices as well. The book I'm showing here, which has the copyright date of 1996, barely mentions wide bandgap materials. So with that, I think I will sign off. And if you have any other questions, you can always send me an email. So good evening, and I hope that tomorrow's sessions with Professor Mohan and Dr. Abhijit Garavagit will be as equally interesting, or if not more so. So I'm going to end the meeting here.